Have you ever wondered what's actually going on inside these incredibly powerful AI models? Well, today, we're going to pop the hood and take a look at the clever architectural tricks that are making them smarter and faster than ever before. Let's jump right in.
So this is the big question, isn't it? It feels like it happened overnight. AIs went from having the memory of a goldfish to being able to process, understand, and remember entire novels, massive legal documents, you name it. How on earth did they get so smart so fast? That's the mystery we're going to unravel.
You see, the whole story really begins with one fundamental problem, a challenge that every single large language model runs into: how to manage its memory. Because as we ask them to remember more and more, this problem doesn't just get bigger, it gets exponentially worse. At the very heart of this issue is something called the KV cache. Now, what is that? The easiest way to think about it is as the AI's short-term memory, kind of like a scratch pad. As it reads through text, it jots down important notes. These are the keys and values, so it doesn't have to start from scratch and reread everything for every single new word it wants to generate. It's a cheat sheet it builds as it goes. But here is the catch. That little scratch pad, the KV cache, it doesn't just grow linearly, it explodes. For a short chat, it's no big deal, but when you ask an AI to remember an entire book, the amount of memory it needs becomes absolutely enormous. And that creates a huge performance bottleneck that can slow everything down to a crawl. So with this massive, exploding memory problem, what do you do? Well, the smartest engineers in the field didn't find one single magic bullet. Instead, they developed a series of really brilliant engineering hacks to make the AI's memory work a whole lot smarter. We're going to pull back the curtain on 3 of the most important ones. Now, the names might sound a little technical, I know, but the ideas behind them are actually pretty intuitive. We've got grouped query attention, sliding window attention, and multi-head latent attention. Let's break down how each one of these clever tricks works. All right, first up to bat is hack number 1, grouped query attention, or GQA for short. This is a really popular efficiency trick you'll find in cutting-edge models like Llama 3. So picture this. The old way of doing things, multi-head attention, was like having a classroom where every single student takes their own, separate, super detailed set of notes. I mean, you can imagine how redundant and wasteful that is. GQA is the smart fix. It's like putting those students into study groups. Now, a small group shares one master set of notes. By sharing that information, you dramatically shrink the amount of memory you need. Simple, but so effective. Okay, on to our second hack. This one's called sliding window attention, and it's all about giving the AI a smart kind of tunnel vision. And, believe it or not, that's a good thing. It gives a huge boost to speed. The old method was just absurd when you think about it. It was like, to understand the sentence you're currently reading in a book, you had to go all the way back to page 1 and reread the entire thing up to that point, every single time. It's thorough, sure, but unbelievably slow. Sliding window attention says, hey, why don't we just focus on the last few pages? You know, the recent context that's most relevant to what's happening right now. The savings in computation are just massive. And that brings us to our final and, honestly, most sophisticated hack, multi-head latent attention, or MLA. This one is a total game changer when it comes to compressing the AI's memory. Think about it this way. The old memory system was like a giant, uncompressed digital photo. It's huge, high quality, but really clumsy to work with. What MLA does is act like a compression tool, like a zip utility. It takes that huge memory scratch pad, finds the most critical information, and packs it down into a tiny, highly compressed file. Then, whenever the AI needs to recall that info, it just quickly unzips it. It's a genius way to save a ton of space. So let's just quickly compare these 3. You have GQA and SWA, which both give you high memory savings, but maybe with a tiny dip in performance. But then there's MLA. Wow. It delivers very high savings while keeping performance similar, or in some cases, even making it better. Now, it's definitely more complex to build, but you can see why that's such a powerful trade-off. Okay, so we've got all these amazing tools in the toolkit. What's the next logical step? Well, the latest trend isn't to just pick one of these hacks. It's to combine them, to build powerful new hybrid models. The whole idea is to get the best of all worlds. Architects are getting really creative, mixing and matching these techniques inside a single AI. For example, they might stack a bunch of those super fast, efficient layers that only look at recent events, and then, every so often, they'll insert a super powerful layer that can read the whole book to make sure no crucial details are missed. The goal is simple: get a massive memory capacity, but at a reasonable price. And what does all this clever engineering lead to? Well, it leads to this: 1 million. Thanks to these hybrid strategies, we're now seeing models that can handle context windows of up to 1 million tokens. A token is roughly a word. So we're talking about an AI that can hold several full-length novels in its short-term memory all at once. That is a staggering leap forward. Okay, this is all fascinating from a tech perspective, but let's bring it back down to earth. Why should you actually care about any of these architectural hacks? What's the so what here?
Well, it's simple, really. A bigger memory directly translates to a more capable, smarter AI. These aren't just small improvements. They are the key that unlocks the ability for AI to tackle truly complex, real-world tasks. We're talking about an AI that can analyze a company's entire financial history in one go, or power sophisticated AI agents that can plan and execute projects all on their own. This quote really gets to the heart of the puzzle that drives all of this innovation. The demand for more and more memory, for longer context, is relentless. But compute resources are not infinite. So the central challenge is always this: how do you keep these models affordable and efficient as they get bigger? And as we've seen, these hacks are the answer to that puzzle. They are the practical, ingenious solutions that let us have our cake and eat it too: massive scale and efficiency. And they're the reason the future of truly powerful AI is becoming a reality much, much faster than most of us ever thought possible. So this leaves us with one final big thought to chew on. We are getting incredibly good at solving this memory problem. As an AI's ability to remember starts to approach something that feels, well, almost infinite, what are the next grand challenges we're going to ask it to solve? What new frontiers will this unlock? It's definitely something to think about.